In this video, we're going to be talking about absolute value equations and inequalities. So let's start by defining what is absolute value. When you've seen absolute value in previous math classes, you probably saw it as something that makes negative numbers positive and then just leaves positive numbers unchanged. This is technically true, but this is not the entire definition of absolute value. So we're actually going to take it one step further and look at it a little bit more in depth. So you can keep in mind this old definition. This is technically still true, but we've got a little bit more to add. So our new definition is that absolute value represents a number's distance from zero on a number line. So if we were to start at zero and travel to our given number plotted on a number line, it's the distance we'd have to travel to get from zero to that number. That's what we're going to define as absolute value. So how do these two definitions relate? Well, we need to make an important distinction. Distance versus another quantity, which we call displacement, is always defined as positive, regardless of which direction we're traveling. So a way to think of this is think about the odometer on your car. So say you get in your car, and we're going to assume you start at what we're thinking of as the point representative of zero on the number line. Say you travel 5 miles north. So you get in your car, you drive 5 miles due north. We know that your odometer adds on 5 miles to your previous mileage total. Okay, so say you've gotten to 5 miles north, and then you turn right around, and using the same route, just the opposite direction, you travel 5 miles south. So you get back to where you started. If your odometer were calculating displacement, it would have added 5 miles for your northward travel, and then when you traveled southward along the same route, it would actually subtract the 5 miles you traveled. Displacement is a quantity that takes into account which direction you're traveling. So if you travel in one direction and then turn around and travel in the opposite direction, your travel times essentially cancel each other out. Well, we all know that's not the case. If you travel 5 miles north, it adds 5 miles. If you travel 5 miles south, it adds another 5 miles. That's because your odometer is calculating something involving distance, and distance is always positive. So we're always adding on when we're calculating with distance. So regardless of which direction we're traveling, whether it's north or south, or for our purposes, we're going to think of it as the positive direction and the negative direction, regardless of which direction we're going from zero, we're always traveling a positive distance. This is how the old definition and the new definition are related. Negative becomes positive, positive is unchanged. Well, that's because we're talking about distances, and distances are always positive, whether we're going in the positive or the negative direction. So this distance definition, this is the one we're going to refer back to for our purposes from here on out. So the notation is something you're probably familiar with. You take a number, you put vertical bars around it. The vertical bars represent absolute value. So when we see those vertical bars around some number, again, we're going to think of it in terms of distance. So whatever that number is, it's how far we'd have to travel starting at zero to get to that number on a number line. Okay, let's look at a couple of examples involving absolute value. So we want to find the given absolute values: absolute value of 3, absolute value of -3, and absolute value of 0. So for absolute value of 3, here's our number line. We want to get to 3 from 0. So we start at 0, we go to 1, 2, and then 3. So we've traveled 3 units, in this case in the positive direction. So the distance traveled from 0 to 3 is 3. So the absolute value of 3 is 3. Now what about the absolute value of -3? Here's our number line, here's -3. So we're going from 0 to -3. So 0 to -1 to -2 and then to -3. Well, in this case, we're traveling in the negative direction, 3 units in the negative direction. However, we decided that when we talk about distance versus displacement, regardless of whether we're going in the positive direction or in the negative direction, our distance is always a positive number. So all we care about is how many units we traveled, not the fact that we're going in one particular direction versus another. So we traveled 3 units, which means our absolute value for this one is also 3. Now what about the absolute value of 0? Well, here's our number line, here's 0. How far do we have to go to get from 0 to 0? Well, it almost doesn't even make sense to ask a question like that. We're already at 0, so we don't have to go anywhere. That means our absolute value of 0 is 0. So now let's talk about absolute value equations. There are always two numbers that share the same absolute value. That's actually what we just saw in the previous example. If we start at 0, we can travel the same distance in either direction and we get to two different numbers. So again, if we're thinking of distance as representing absolute value, then two numbers are the same distance away from 0. In other words, two numbers have the same absolute value. So we're going to use this idea to solve equations involving absolute value. So the most basic case is something of the form absolute value of x is equal to a. We're going to think of x as the variable we're solving for, and then a is going to be an actual constant number when we're looking at a problem. So sometimes it's helpful to think of this as a question. So if we think of this equation as a question we're trying to answer, the question is, what number or numbers represented by the variable x is or are a distance of a units away from 0? So in other words, if we start from 0 and we want to get to whatever this number x is, we can go a units in either direction, and that takes us to the two possible values for x. So this leads to actually two equations when we're trying to solve an absolute value equation. It actually leads to two particular parts that give us two values as part of our solution. So if absolute value of x is equal to a, whatever x is, its distance from 0 is a units. So we can travel a units in the positive direction, or we can travel a units in the negative direction, and we'll get to two different numbers that have the same distance from 0. So this means that x is either equal to a or x is equal to negative a. This means we have two solutions for this particular equation. So let's look at a really basic example first. We want to solve the equation and then graph the solution on a number line. And our equation is absolute value of x is equal to 4. So again, if we want to think of this as a question, the question is, what number or numbers represented by the variable x are a distance of 4 units away from 0. So we know that distance is positive, but we can travel that positive distance in either direction, but we just have to travel 4 units. So this means x is equal to 4 or x is equal to negative 4. Both the numbers 4 and negative 4 are 4 units away from 0. So our two solutions are 4 and negative 4. In terms of set notation, this is the official way to write a solution to a problem like this. When you can list out a finite number of solutions, you write in set notation. So it's just a list of the answers to our problem written in curly braces. So I've written negative 4, 4. It's traditional to write smallest to largest, but one of the special things about set notation is that you can actually write things in either order. So if I write negative 4, 4, that's the same thing as if I write 4, negative 4. Both of those solutions represent the same set. You can write in either order and it doesn't matter. In terms of our graph, on a number line, we just plot our points where our solutions are, so at negative 4 and at positive 4. Now we're going to take it one step further. So we want to solve just general absolute value equations. The same ideas apply when the equation becomes more complicated. So in other words, when we're adding on other numbers in the problem, maybe there's numbers multiplied by the absolute value or added or subtracted onto the end of the absolute value, the same ideas still apply with one additional component. So it's important that we isolate the absolute value before applying that distance definition. We can't use the definition unless the absolute value is by itself and it's equal to a number. Another way to think of this is you cannot touch the inside of the absolute value until you get it by itself. So my trick for remembering this particular idea is birthday present. So it sounds really silly, but it'll help, I promise. So with a birthday present, you have to unwrap it before you can get into the box and see what your present is. So think of what's inside of the absolute value as your gift. It's wrapped up in a box. Well, the box is the bars around the absolute value. So it's in the box. You can't get into it until you open the box. But you can't even get to the box until you peel off the wrapping paper. So the wrapping paper is all the stuff that's on the outside of the absolute value. So if there's anything multiplied, divided, added, or subtracted outside of the absolute value, that represents the wrapping paper. All the wrapping paper has to come off first before you can open the box. In other words, before you can split up the absolute value. And then, and only then, can you actually get into the box and start to enjoy your gift, which in this case is the number we're solving for. So let's look at a couple examples of more complicated absolute value equations. So we want to solve the equation, and then just like before, we want to graph the solution on a number line. So our first equation is 4 times the absolute value of 2x plus 7 plus 2 is equal to 22. So first thing we need to do is we need to isolate the absolute value. In other words, think again, birthday present. So we want to get 2x plus 7. That's what we care about. That's the gift. It's in a box represented by those bars, and then there's some wrapping paper on the outside. Well, in this case, the wrapping paper is the 4 multiplied out front and the 2 added on to the end. We have to pull off the wrapping paper before we can get to the box, before we can open the box. So here's our equation. We've got to get rid of the 2 first. So if there's a multiplication and an addition or a subtraction, the addition/subtraction has to go first. So to get rid of the added 2, we subtract from both sides. Then we have that 4 out front. Now I want to caution you here. It's really tempting to say that this is a distributive property situation. It's really tempting to say, okay, well there's a 4 out front. I can distribute it to the 2x, I can distribute it to the 7, and then it goes away. I'm done with it. Unfortunately, you can't do that with absolute value. So if those were parentheses around the 2x plus 7, yes, you could do that. Absolute value bars don't function the same way parentheses do. So although they separate the 2x plus 7 from the rest of the problem, stuff that's inside the bars stays on the inside, stuff that's on the outside stays on the outside. They don't mix. So in order to get rid of the 4, we can't distribute it, we have to divide it. So divide it from both sides. So we're left with the absolute value of 2x plus 7 is equal to 5. The absolute value is isolated, we're good. So we peeled off the wrapping paper. Now let's open the box. In other words, we want to split it up into the 2 components and then solve what we're left with. So we have the absolute value of 2x plus 7 is equal to 5. So if we think of this as a question, we're saying some number represented by 2x plus 7 is 5 units away from 0. Well, what could it be? Well, we know if we travel a distance of 5 units, we can travel in either direction. So 2x plus 7, whatever this number is, it's 5 units in some direction away from 0. So it's either 5 units away in the positive direction, in other words, it's equal to 5, or it's 5 units away in the negative direction, in other words, it's equal to negative 5. So we have 2 separate equations to solve that represent the 2 solutions to this problem. Notice that the 2 equations are basically the same except for the right-hand side. One is positive, one is negative. What this means, however, is that the algebra is going to look virtually identical when we solve each equation. We're just going to have a different number on the right-hand side at the end. So let's look at the first one. 2x plus 7 is equal to 5. I've got to subtract my 7 first, and then I divide the 2 out front. I get x is equal to negative 1. We'll use the exact same algebra for the other equation, but again, we're just going to have a different number on the right-hand side. So subtract the 7 and divide the 2. We get x is negative 6. So we want to write our solution set, and then we want to graph it. In set notation, we have negative 6, comma 1, or you could write negative 1, comma negative 6, doesn't matter. And then for our graph, here's our number line. We plot points at negative 6 and negative 1, and that is our graph. Now let's try another one that's slightly more complicated. So same directions, we want to solve our equation and then graph on a number line. Now our equation has some fractions in it. It's okay. The rules still apply in the same way. We're just going to have to deal with the fractions, so we'll deal with them as we come to them. So first step is still the same. We need to isolate the absolute value. So we have that absolute value, but we've got that minus 1/3 tacked on. That's essentially our wrapping paper in this situation. So remember, we peel off the wrapping paper before we can do anything else. So it's a subtracted 1/3, which means it needs to be added to move it to the other side. Problem is, the other side is another fraction, and these 2 fractions don't have the same denominator. In order to add or subtract fractions, we have to have the same denominator. So I need to rewrite both of these in terms of some common denominator. Well, in this case, the least common denominator is 6 because our denominators currently are 3 and 2. The least common multiple between 3 and 2 is 6. So I want to rewrite the 1/3 and the 1/2 as fractions with a denominator of 6. Now, one thing I want you to notice is that there is another fraction in the problem inside the absolute value. We're not going to worry about that yet. All we care about is the two fractions that we need to combine. Let's just leave the other one alone. So 1/3 becomes 2 over 6, 1/2 becomes 3 over 6. Now that our fractions have the same denominator, we can add the 2/6 to both sides. We combine their numerators, and then we have 5/6 on the right-hand side of the equation. So our absolute value is isolated. We're in a good position to continue. So we peeled off the wrapping paper. Now we need to open the box. So here's our equation. Absolute value of 4 minus 1/2 x is equal to 5/6. So it doesn't matter that we have fractions. The idea of absolute value representing distance works the same way regardless of what numbers we have in our problem. So we're saying this mystery number, represented by 4 minus 1/2 x, is 5/6 units away from 0. So again, we can travel 5/6 in either direction, and we've traveled the same distance. So this means that 4 minus 1/2 x is either equal to 5/6 or it's equal to negative 5/6. Same distance, just opposite directions. Now we have two equations and they both have fractions. So I'm going to show you a trick for how to get rid of the fractions at this point. This trick wouldn't really apply to the previous part where we were trying to get rid of the other fractions, just because it would make the equation more complicated than it needs to be. But at this point, x is easy to solve for. We're just trying to get x by itself, so this trick will apply. So what we're going to do is we're going to multiply through both equations by the least common denominator, and that's actually going to eliminate all our fractions. So the two fractions we have in each problem are 1/2 and 5/6, just differing in sign. So our least common denominator is 6. So we're going to multiply each equation on both sides by 6. Something special happens when we do that. So because 6 is a common denominator between 2 and 6, if you were to distribute the 6 throughout the problem, all the denominators actually cancel out. So if you need to, take a moment and write this down, do it yourself, do it manually, and make sure you get what we got. So we end up with 24 minus 3x is equal to 5, and then 24 minus 3x is equal to negative 5. Again, basically the same equation, just the right sides differ. So now we need to solve for x in each case. Let's start with the left-hand equation. So we want to get the x by itself. We have a positive 24 out front, so we need to subtract 24. Then we need to divide our negative 3. So we get x is equal to positive 19 over 3. Same thing on the other side, same algebra, just a different right-hand side of the equation. So subtract the 24 and then divide by the negative 3. So x is equal to 29 over 3. So these are our two solutions. So in set notation, same thing. Typically we write smallest to largest, but again, order doesn't really matter. Now, I want you to leave your solutions as improper fractions. That's technically okay. We call them improper, but they're still proper. They're still okay. For graphing purposes, though, you might want to plug those into a calculator and see where they approximate in order to graph them. So 19 over 3. Well, 3 goes into 19. Let's see, it goes in, I guess, 7 times. 3 times 7 is 21. No, so 3 times 6 is 18. So it goes in 6 times evenly with a little bit left over. So 19 over 3 is going to be somewhere between 6 and 7. What about 29 over 3? Well, 3 times 9 is 27, 3 times 10 is 30, okay? So 29 over 3 has got to be somewhere between 9 and 10. So we have something between 6 and 7, something between 9 and 10. Your graph doesn't have to be perfect, you just need to be between the correct units, and that's perfectly fine for a graph. Let's finish up our equations by looking at a couple of special cases. So we want to do the exact same thing we've done before, and we're going to start out just like any other equation. So we have 6 is equal to 7 plus the absolute value of 9x minus 3. So in absence of any other information, this is just an equation. I'm going to treat it exactly like I treated the previous equations. I have to isolate the absolute value, then we'll split it up and solve. So my wrapping paper in this case is that 7 added on front. So I need to subtract the 7 to isolate the absolute value. So I'm left with -1 is equal to the absolute value of 9x minus 3. You could flip the order if you need, it doesn't really matter. So let's think about what we have right here. We have absolute value of 9x minus 3 is equal to -1. Well, we have to again think about what absolute value means. It means distance from 0. So whatever the number 9x minus 3 is, the number on the other side of the equation represents its distance from 0. Well, we have a problem. Because absolute value represents distance, distance has to be positive. But we're saying that this absolute value, this distance, is equal to a negative number. That's a problem. Well, what does that mean for our purposes? What does it mean for x? It means there's no solution. So absolute value always has to be equal to a positive number because it represents a distance. So if you have an equation, once the absolute value is isolated, if it is isolated and equal to a negative number, that means there is no solution for this equation. There's no value of x that would make this equation true. So that is one special case for absolute value equations. Once the absolute value is isolated, if it's equal to a negative, there is no solution. Now let's look at another special case. So same thing, just solve the equation, but now let's put two absolute values into our equation. So we have absolute value of 4 minus x is equal to absolute value of 2x plus 1. So we actually have two distances in this problem. Well, we need to think about what this equation is really saying. Since absolute value represents distance, this means that whatever 4 minus x and 2x plus 1 are, because we're taking the absolute value of each, and both of those absolute values representing distance, by setting them equal, we're saying that those two numbers are the same distance from 0. That's what this equation means if we were to translate it into a question. It means what are these two numbers so that their distance from 0 is the same? Well, there's two ways that this could happen. Either 4 minus x and 2x plus 1 are the same number. That's one possibility for them to have the same distance from 0. Or the other possibility, so that they would have the same distance from 0, is that they're opposites. So one of them is going to be the positive version of a number. One of them is going to be the negative version of the same number. So they're different numbers, but they're the same distance from 0. So what does this mean for the purposes of splitting up our problem? Well, it means either they're the same, which means 4 minus x is equal to 2x plus 1, or they're opposites, which means 4 minus x is equal to the negative version of 2x plus 1. So the first one's pretty straightforward. If they're the same, they're equal. For the second equation, notice I put parentheses around the 2x plus 1. If we're saying they're opposite, in order to make an entire number opposite, we have to make the entire number negative. Well, the entire number is represented by 2x plus 1. So in order to take the opposite of 2x plus 1, we have to apply a negative to all parts of the number. So I put parentheses around the 2x plus 1, put the negative out front, and that makes that entire number negative. In other words, we take the opposite of that entire number. At this point, we treat it the same as we treat any other problem. So we're trying to solve for x. So let's look at the left-hand equation. Notice I've got x's on both sides of the equation now, so I need to combine like terms, get x by itself. So first thing, one option is if you take that negative x on the left, add it to the 2x on the right, we then have 4 is equal to 3x plus 1. Okay, we're trying to get the x by itself, so I need to move that plus 1 over to the left-hand side. So subtract 1 from both sides. We get 3 is equal to 3x. Divide by your 3, and you get x is 1. That is one solution to our problem. Now let's look at the other one. So first thing I need to do here, because I've got that negative outside those parentheses, parentheses not absolute value bars, we are going to distribute that negative in on the right-hand side of the equation. So 4 minus x is then equal to negative 2x minus 1. Now we're going to do the same thing we did before. You don't have to do the same order. You can move things around, but we need to get the x's on one side. We need to get all the constants on the other side. This time, I'm going to add the negative 2x instead of adding the negative x. The reason I like to do this is because that means I then have a positive x. I don't have to deal with any negatives in front of the x. If you just add the negative x, you're still going to have a negative x on the right-hand side of the equation. So it'll still work out for you either way, but you just might have one more step in your algebra. So we have 4 plus x is equal to negative 1. Got to move the 4 over, so subtract the 4. So we get x is negative 5. These are our two solutions. So in set notation, the solution is negative 5, comma 1. Now that we've talked about equations, let's talk about inequalities. So we're going to split inequalities up into two parts, what I'm going to call case 1 and case 2. So the basic case for case 1 is that we've got an absolute value that's less than or equal to a number. So whenever we have a less than or less than equal to, these particular rules apply. So again, think of it as a translation of a question. What number or numbers represented by the variable x is or are less than a units away from 0? So now what we're saying is we want to go from 0 to a number, but we don't have to travel an exact amount. We just have to travel less than a certain amount. So if you visualize what this means in terms of what we talked about with traveling and recording on your odometer, you're starting at 0, you're starting at a point, and say you want to travel less than 5 units. Well, that means you can travel either direction. You can travel north or south, and you could travel 1, you could travel 2, you could travel 2.5, you could travel pi units. Pi is still technically less than 5. You just can't travel past 5 units in either direction. So one thing that's different here is we're not going to have just one or two solutions. We actually have a bunch of possibilities that could solve an inequality. All they have to be is less than a units away from 0. So in order to split this up for each of our situations, we know that we can travel a units. We can travel out to a in the positive direction. We can travel out to a in the negative direction. We just can't travel any further. So when we split it up, we still have the same endpoints, negative a and a, but x just has to be between those numbers. So it's not identically equal to either of them, it's just between them. The only thing that changes when we add on the equal to is our less than symbols then become less than or equal to symbols. So for each of these, we're saying x is greater than the negative endpoint, x is less than the positive endpoint, so it has to stay between those. So let's look at an example. We want to solve the inequality and then graph our solution on a number line. So our inequality is absolute value of x is less than negative 4. So we're saying whatever this number x is, it has to be less than 4 units away from 0. So we could travel out to 4 in the positive direction. We could travel out to negative 4 in the negative direction. We can go anywhere between those. We just can't go past those. So that means that x has to be between negative 4 and 4. So one thing that's going to change when we start talking about inequalities is the way we write our solution. So we're going to use set notation, but set notation looks a little bit different here. With our basic set notation where we're just listing out one or two numbers, just a finite set of numbers, we use curly braces. Well, we don't actually have a finite number of solutions here. We actually have an infinite number of solutions. Any number between negative 4 and 4 would be a solution to this inequality. So the way we write that particular set, what we call an interval, it's the interval from negative 4 to 4, all the things between them. We write the two endpoints, negative 4 and 4, write a comma, that's to indicate we want to include everything between those two numbers. And because we're not including our endpoints, we're not including negative 4 and 4 as part of the solution, they're just the imaginary endpoints, we use parentheses around the endpoints. So parentheses, negative 4 to 4, and then close parenthesis means that we can have every point from negative 4 to 4, but not including those actual endpoints. So once we have the set notation, the graph is pretty much identical. So if you've graphed inequalities before, you've probably used open circles and closed circles. We're going to change that up a little bit. We're actually going to use parentheses and brackets instead. So same thing with our endpoints. It's negative 4 to 4. But at our endpoints, we're just going to put parentheses. So if you've done this before, you would have seen open circles there at -4 and 4. We're just going to put parentheses there instead. Otherwise, it means the exact same thing. So our solution is the interval containing all the values between -4 and 4. Let's try another one. So same situation, but now let's do absolute value of x is less than or equal to 4. So we're saying whatever x is, it has to be less than or equal to 4 units away from 0. So we can travel to 4 in the positive direction, -4 in the negative direction. The only difference is now we can actually end up at those endpoints. We can stop at those endpoints as opposed to having to stop just short of those. So that means that whatever x is, it's between -4 and 4, including those endpoints. Well, what changes with our solutions? In our set notation or our interval notation, we change from parentheses to brackets. Brackets indicate that we can include the endpoints as part of our solution. Same change with the graph. So here's our number line. We want everything from -4 to 4. Here we can include -4 and 4, so we put brackets there. Now let's look at a slightly more complicated example involving an inequality of the less than or the less than or equal to variety. So same directions, we want to solve the inequality and then graph on a number line. So 2 times the absolute value of 6 minus x minus 3 is less than 7. The rules for equations still apply to inequalities, so the whole birthday present idea, that still applies. So first thing we need to do is isolate the absolute value. So we've got a 2 multiplied out front, we've got a 3 subtracted on the end. First thing I need to do is move the 3 over. So add 3 to both sides, we get 2, absolute value of 6 minus x is less than 10. Now we need to divide the 2. Remember, you cannot distribute it, you have to divide it out. Divide from both sides, we get absolute value of 6 minus x is less than 5. So we've peeled off the wrapping paper. Now we need to open the box. So what this inequality is saying, it's saying that whatever number 6 minus x represents, this number is less than 5 units away from 0, strictly less than 5 units. That means we can go 5 units in either direction, either out to -5 or out to +5, but we have to stay between those. We can't be equal to them. We just have to be somewhere between them. So we essentially write a little sandwich with -5 and 5 on the ends. So one thing I want you to notice here is, yes, we do have the 2 endpoints, but as opposed to writing 2 separate statements and solving 2 individual equations or inequalities, we're actually solving 2 in tandem. So this particular inequality has 3 parts. It has the middle part where there's the x we're solving for, and then it has something on the left hand, and it has something on the right hand. What you have to be mindful of when solving a problem like this is anything you do to one part of this inequality, you have to do to the other parts as well. So the goal is to get rid of the x. Anything we do to remove stuff from the x, we have to do to the left-hand endpoint and to the right-hand endpoint at the same time. So just be aware of that. So we want to get x by itself. We've got a 6 out front. Even though it's 6 minus x, the 6 is positive. So to get rid of a positive 6, we have to subtract it. So subtract the 6 from all 3 parts. So -5 minus 6 is -11, and then 5 minus 6 is -1. So we now have -11 is less than -x is less than -1. Notice that negative in front of the x in the middle just goes with it. We haven't gotten rid of it yet. So that's the last thing we need to do. We need to get rid of that. It's multiplied, so we need to divide it. There is a special consideration here, though. You might remember with inequalities, whenever you divide or multiply by a negative, you flip the inequality signs. So in this case, we're dividing by a -1. We divide like normal, but our inequality signs have to be flipped in the opposite direction once we divide. So we then end up with 11 is greater than x is greater than 1. So x is by itself, but we have a little bit of a problem. This is not an easy way to write a solution. Typically, you want your smallest number on the left, your largest number on the right. Well, there's a trick here. An inequality can be rearranged as long as the arrows are pointing toward the same numbers. So we want our smaller number on the left, our larger number on the right. We can do this as long as the arrows and the inequalities are pointing towards the same number. So notice we have one pointing towards 1 and then it's eating, for lack of a better way to put it, it's eating the x. And then we have one pointing towards the x and then eating the 11. We have them written such that the 11 is on the left and 1 is on the right. We can flip them as long as we're still pointing towards the same numbers. So even though the arrows are pointing in the opposite direction, they're pointing towards the same numbers. So this is legal to do. So our final inequality is 1 is less than x is less than 11. So 1 and 11 are our endpoints. For our solution set in interval notation, it's 1 to 11. So 1 and 11 are our endpoints. Because there's no equal to, we're using parentheses. And then on our graph, we're essentially going to write the same thing using endpoints of 1 and 11 with parentheses. That's our graph. Let's look at another one. Same directions. Now we have -4 is less than or equal to -2 times the absolute value of 3x plus 1. Start out, isolate the absolute value. So we've got a -2 in front of our absolute value. It's got to go away. We have to divide it. So we divide both sides, but this is an inequality. We're dividing by a negative, so when we divide it, we flip our inequality sign. So now we have 2 is greater than or equal to absolute value of 3x plus 1. Well, this seems like a problem. We've been dealing with less than or equal to. This is greater or greater than or equal to. Well, it's actually not a problem because we have that trick from the previous example. Remember, if we want to rewrite an inequalities order, as long as things are pointing towards the same numbers, we can flip the order and having pointing in either direction. So our arrow is pointing towards our absolute value and then it's eating the number 2. So we can flip the order as long as we're still pointing towards the absolute value and then eating the 2. Now we're in the situation we need to be in. So absolute value of 3x plus 1 is less than or equal to 2. Now we need to split it up, open up the box. So we're saying whatever this number 3x plus 1 is, it's less than or equal to 2 units away from 0. So its distance from 0 has to be less than or equal to 2 units. So we can go 2 units in the positive direction, we can go 2 units in the negative direction, we can go anywhere between them, we just can't go past them. So we have -2 is less than or equal to 3x plus 1 is less than or equal to 2. Just like before, we have 3 parts to this inequality. Whatever we do to one part, we have to do to the other 2 as well. So the goal is to isolate the x, which means we need to get rid of the 3, we need to get rid of the 1. So subtract the 1 first. So -3 less than or equal to 3x less than or equal to 1. And then divide the 3. So -1 is less than or equal to x is less than or equal to 1/3. That is our final inequality. So in interval notation, it's -1 to 1/3 with brackets because we have the equal to in this case. And then our graph is everything from -1 to 1/3 contained using brackets. Now let's look at our final case. So we've looked at equations, we've looked at inequalities with less than or less than equal to. So our final case is inequalities with a greater than or a greater than or equal to symbol. So again, if we want to think of this as translated into a question, the question is what number or numbers represented by the variable x is or are more than a units away from 0. So now if you think about it in terms of the odometer example, we could travel 5 miles north, we can travel 5 miles south, but where we end up has to be more than that many units away from our starting point. So we have to drive mile 1, we have to drive mile 2, etc. But where we stop has to be more than 5 miles from where we started. We have to go out past 5 miles north or out past 5 miles south. We have to go more than a units away from 0. So when we split this up, these particular problems are actually going to have 2 completely separate components. So if our distance is more than a units away, remember we can travel in either direction and still be traveling a positive distance. So we can travel to where we're less than -a or more than positive a. So something that's more negative than our negative endpoint or more positive than our positive endpoint. The only thing that changes when we add the equal to is our solution has equal to's as well. So if we're thinking in terms of the car example, we can stop at 5 miles versus not being able to stop at 5 miles. Let's look at a couple of basic examples. So we want to solve and graph like before. Our first example is the absolute value of x is greater than 4. So we're saying whatever x is, it has to be more than 4 units away from 0. So we can go more positive than positive 4 or more negative than negative 4, and either of those can be the point where we stop. So either x is less than negative 4 or x is greater than positive 4. Notice these are going to be two completely separate components on tails of our number line. So what do our intervals look like? Well, we have everything from negative infinity to negative 4, not including negative 4, and then we have everything from 4 to infinity. So let's look at the intervals in a little more depth. Notice with the negative infinity and the infinity, I put parentheses around those. Whenever you have an infinity or a negative infinity, you have to use parentheses. You cannot use brackets. You can only use brackets when something is an actual number. Infinity is not a number we can reach, therefore we just use parentheses around it. Having an infinity is just saying that our interval continues forever. It never stops. Also notice that the order here is very important. So with a set, when we're just making a list of numbers that could be possible solutions to a problem, we can write in any order and it doesn't change our answer. With intervals, something like this, we have to write the smallest number to the left and the larger number to the right. That's very, very important. So for our first interval, negative infinity is less than negative 4, so we write negative infinity on the left. For our second interval, positive infinity is greater than positive 4, so we write the positive infinity on the right. Also notice that symbol in the middle between the two intervals. It looks like a U. That's called the union symbol or the join symbol. It's just a nice way of saying we have two separate parts of our answer and we want to take them both as the entire answer. So if we want to combine two intervals together and include both of them, we put this union symbol between them. If we wanted to have 3 intervals on our solution, we could have 3 and just put 2 big U symbols in between them. So that's our set notation. What about our graph? So we have everything from negative infinity to negative 4. In other words, everything to the left of negative 4 on the number line is fair game. And then everything from 4 to infinity on the right-hand side, everything from 4 on upwards to the right-hand side of the number line is also part of our solution. What happens when we change to greater than or equal to? Well, now we're saying our distance traveled has to be greater than or equal to 4 units. So the only real difference is that now we can stop at 4 as opposed to being required to go strictly past 4. So x can be less than or equal to negative 4, or it can be greater than or equal to positive 4. The only thing that changes in our set notation is we now have brackets around negative 4 and 4. Notice that the parentheses with the infinities did not change. They are completely independent of any of the other symbols in our intervals. Regardless of what else we have, the infinities still have to have parentheses around them. And then the only thing that changes with our graph is also the parentheses change to brackets. So we can now include negative 4 and 4 as opposed to those being non-included endpoints. So now let's look at a couple more complicated examples. So again, we want to solve and graph. So we have 2 times the absolute value of x plus 3 minus 4 is greater than or equal to 6. Just like with any other problem, we follow the same series of steps. So we need to isolate our absolute value. In this case, we've got that negative 4 and we have a 2. Got to add 4 to both sides and then divide 2 on both sides. So our isolated absolute value inequality is absolute value of x plus 3 is greater than or equal to 5. So we peeled off the wrapping paper, now we have to open the box. So what we're saying here is we're saying whatever x plus 3 is, it's more than 5 units, it's more than a distance of 5 units away from 0. So we can travel out past 5 in either direction, but we can't stop anywhere in the middle. So we have 2 cases. Either x plus 3 is less than or equal to negative 5, in other words, more negative than negative 5, or x plus 3 is greater than or equal to positive 5, in other words, more positive than positive 5. This situation is a little bit different than our previous case with inequalities. There's no way we can combine these two into a single inequality because as we saw from the previous graphs, they're completely separate. They're on ends of the number line. Whereas with our previous problem with the less than or equal to, it was one interval that was in the center of the graph. Because these are separate, they have to be written as completely separate inequalities. But again, the algebra looks basically the same, just like it did before. So subtract our 3 from both sides, we get x is less than or equal to negative 8, and then x is greater than or equal to 2. So these are going to be our two inequalities corresponding to two intervals for our solution. So everything less than or equal to negative 8 is everything from negative infinity to negative 8. Because there's an equal to, we put a bracket with a negative 8. And then our second inequality, x is greater than or equal to 2, is everything from 2 to infinity with a bracket around the 2. And then our graph is everything on the tails of the graph with endpoints at negative 8 and at positive 2. Let's look at another one. So negative 18 is greater than negative 3 times the absolute value of 2x minus 4. So need to peel off the wrapping paper first, isolate the absolute value. We have that negative 3 in front of the absolute value, so that has to go away. We're dividing by a negative 3. When we divide by a negative, we flip the inequality sign. So we now have 6 is less than absolute value of 2x minus 4. Just like usual, we like to have the absolute value on the left-hand side and then the number on the right. And as we discussed before, we've decided that as long as our arrow is pointing towards the same numbers, we can write the arrow in either direction. So it has to be pointing towards the 6 and then eating the absolute value. So if we flip this, its absolute value of 2x minus 4 is greater than 6, and then we're ready to proceed. So now we want to split it up. So we're saying whatever 2x minus 4 is, it's a distance of more than 6 units away from 0. So either it's less than negative 6, in other words, more negative than negative 6, or it's greater than positive 6, more positive than positive 6. So now we solve each of these inequalities. Add your 4, so we have 2x is less than negative 2. Divide by 2, so x is less than negative 1. Same thing on the other side, so add the 4, 2x is greater than 10. Divide by 2, x is greater than 5. So translated into interval notation, we have everything less than negative 1, but strictly less than negative 1, which means we use parentheses instead of brackets. Then we also have everything greater than 5, so everything from 5 to infinity, again with parentheses. On our graph, we have intervals from negative 1 to negative infinity, in other words, the left-hand tail of our number line, and then everything from 5 to infinity, the right tail of our number line, using parentheses. To summarize, we have three situations. The first, absolute value of x is equal to a number. So either x is the number itself or it's the negative version of that number. Those are the two ways we could go an exact distance of a units away from 0. In this case, our graph is just two individual points graphed on a number line. The second case is the absolute value of x is less than a specific number. So this means we could travel up to a units in either direction, but we can't travel any further. So x has to be between negative a and a, whatever those two endpoints are. In this case, our graph is an interval centered around 0 with negative a and a as endpoints. If we add an equal to our original inequality, we change our parentheses to brackets on our graph. And finally, absolute value of x is greater than a. So whatever x is, it has to be more than a units away from 0. So we can either go more negative than negative a, or we can go more positive than positive a. In either case, we have tails on our graph, on our number line. So we can have everything to the left of negative a, everything from negative a to negative infinity, everything on the left, or everything on the right from a to positive infinity.